Good day, everyone. My name is Dr. Kalagbor. I'm the lecturer for STC 414, Analytical Chemistry 3. The topic for today is voltammetry. And for this course, STC 414, the syllabus has given us some general objectives, and we have covered some of them. There are three objectives. The first objective is on the principles, design, operation, and applications of immunoassays. And you remember we had the ELISA kit, with which we did our studies. And then the second objective is the basic principles and applications of automation in the laboratory. We looked at the use of robotics, and then some of the analytical methods that can be used, like the flow analysis. And that is a picture of the robotic arm being used in a lab. And then the last objective is the general principles, operation, and applications of electroanalytical methods. Here there are three analytical methods that we need to know about: potentiometry, amperometry, and voltammetry. The first two we have studied, and of course you remember you came across this. This is one of the typical titrations that is observed in potentiometry. So now for today's topic, we are going to talk on voltammetry. But before we can take this lecture, we need to understand what voltammetry is all about. Now, voltammetry is an electrochemical method that is based on measurement of current as a function of the potential applied to a tiny microelectrode. The emphasis is on microelectrode. Now, one form of voltammetry is polarography, and this is based on the measurement of current of an electrochemical cell using a drop-in working mercury electrode known as the DME, the drop-in mercury electrode. And of course, the potential is varied continuously. Now, when you look at this diagram, it's a typical apparatus for polarography. Now, the working electrode, like I said, is the drop-in mercury electrode. Now, for emphasis, I'll show you that is the mercury drop coming from this. Now, you have the Kalagbor reference electrode, you have the working electrode, which is the drop-in mercury electrode, and of course, you have the counter electrode. That's why polarography is said to work as a 3-electrode system or 3-electrode cell. Now, when your analysis is being carried out, your result shows a linear scan voltammogram, and that is what I'm going to put on the board for you to see. Now you have your current. Of course, this is the voltage, okay? Voltage versus this saturated Kalagbor electrode, which is your reference electrode. And this is your current axis. Okay, microamperes. Now, when you start your analysis, you know, the potential is in the negative. So you have your negative values, and so on and so forth. Now, when you start, most often your current is a bit constant. This is the residual current. At a point where the electroactive species begin to be detected in your analysis, you notice that the current starts rising. There's a sharp increase, and then at a point, it stabilizes and becomes constant. And this is what you will see. Okay? Now, this residual current which you have observed at the beginning is this. And the stage where it becomes constant, you refer to it as your limiting current, which is your LC. Now, between your RC and LC is the range we refer to as the diffusion current, represented by ID. Okay, so now when you look at this and you try to take this shape, first of all, you extrapolate. And if we do the extrapolation, we're going to get a shape that looks like this, and that's what we refer to as the sigmoid curve. And that is the shape of our sigmoid curve. Now, this is a typical polarogram, or what you may refer to as the polarographic wave. Now, you can see that from A to B, we have the current being constant, sort of. That is the residual current. Now, as we detect our species, electroactive species, which is the reduction of the cadmium ion to cadmium metal, you can see that the current begins to increase, begins to rise, and then stabilizes. Now, this is our polarographic wave. And so we say the sharp increase from the residual current to the limiting current, which is the current above, is called a polarographic wave. And this is what we obtain when we do our polarographic analysis. So, like I showed you in the previous slide, LC minus RC. LC here minus RC gives you ID. In polarography, the only mechanism of mass transport is diffusion, and that is why we talk about the analysis in terms of diffusion current, ID. Now, and so an equation for polarographic diffusion current is given by Ilkovic. It's called the Ilkovic equation, and with it we have been able to carry out a lot of calculations in polarographic determinations. And so ID is equal to 607 n d to the power half m to the power 2 over 3 and t to the power 1 over 6 and then c. Now, it's important to know that 607 is a constant that involves the Faraday constant, and we all know what the Faraday constant is. And all these other ones, of course, are the values we get from carrying out the analysis, and of course some of the parameters we have also put in. Now, let's look at a typical problem. Now, this is a 5 times 10 to the power minus 3 molar solution of cadmium chloride in 0.1 molar HCl. Now, it shows that the diffusion current is this. Now, if the mercury, because remember we are using a dropping mercury electrode in our analysis. Now, if the mercury is dropping at the rate of 15 drops per minute, and the rate for the weight of 20 drops is 80 milligram, calculate the diffusion coefficient of cadmium ion in the solution. Now we are going to use the Ilkovic equation, which is ID is equal to 607 n d to the power half m to the power 2 over 3 t, which is time, for 1 over 6, and then the concentration. Now, if we go back to the problem, we have a value for ID. 607 is a constant we already know. N is the charge. And converting cadmium ion, that's the reduction at the electrode, will give us the cadmium metal. And so from this, the value of N is 2. That's what we're going to put there. Remember, D is what we're looking for. That's the diffusion coefficient. So we don't know that one yet. The mass we can calculate from the number of drops of the mercury, and then T we can also get from the drops of the mercury that we have been given, and then of course concentration is also given. Now, if we go back to the problem that we have, of course that's the diffusion current, so that is ID, okay? Then that, of course, is our concentration, so we have C. And then the next entity we have to find from our equation is T and M. So we're going to solve for that. Now, we're going to use the 15 drops per minute to calculate our T, and then the 20 drops giving us 80 milligram to get our mass. All these parameters, of course, have their units. For the ID, the unit has to be in microampere. N is okay. That is in centimeters per second. That's for D. Okay. Then our mass, the unit has to be in milligrams per second. And of course, our concentration we already have as millimoles per liter. Our time is in seconds. Okay, now I've shown you the other ones we have, so let's take them one by one. To us as from our calculation was given to us as 5 times 10 to the power minus 5 amperes, and we have to convert this to microamperes. And so it's going to be 5 times 10 to the power minus 5 times 1 times 10 to the power 6, and if you do this, you're going to get 50 microamperes. So ID is equal to 50 microamperes. We keep that aside. Good. Then the next one we need to convert that we already have, we have N. N, which is the number of electrons that is involved in the reduction of the cadmium ion. And remember, going back to what I showed you before, you have 2 as the value of N. So we have that entity. Remember, our 607 is already there, it's a constant. So the next entity we need to get, D, is what we are looking for. Then the next one we have to find is M, which is the mass. And so we have to do some calculation here. Now, the mass that we're given in this problem is 80 milligrams. And this is 80 milligrams that gives us 20 drops. And then this 20 drops, which is the total from the 80 milligram, is actually dropping at 15 drops per minute. And we know that in this calculation of ID, we don't deal with minutes, we deal with seconds. So we convert the 1 minute to 60 seconds. And then that is where we are. 80 times 15 is going to give you 1,200 milligrams. Remember, drops cancels drops here. And then 20 times 60 seconds will give us what? 1,200 seconds. And so when you divide that, you end up with 1 milligram per what? Second. So now we have the value for M. So M is equal to 1 milligram per second. Now the next entity in our equation, that equation should be somewhere close by, is the value for T. Remember, I told you we don't have T, but we have concentration, which we're also going to convert. And so for us to get T, T says 60 seconds is what we use to obtain 15 drops. So if we have that, then it's going to be 4 seconds. So T is 4 seconds. And then last but not the least is concentration. If we go back to our problem, remember the concentration is 5 times 10 to the power minus 3 moles. So that's our concentration. We have 5 times 10 to the power minus 3 moles. And since we're dealing with millimoles, this we now convert to 5 millimoles. And now we have all the parameters that we need for this calculation. So going back to Ilkovic equation, which says ID is equal to 607 N D to the power half M 2 over 3 T 1 over 6 C. Now we have the values for all the parameters available. For ID, we have 50 microamperes. So we'll put 50 here. We have 607. For N, we know that it is 2. D is what we are looking for. Okay? M, we already have. If you go back, we have calculated for M, and that is the value of M. Okay, so we now put 1, and remember that. So 2 over 3. And then T we have also solved for, which is 4 seconds, times 4, remember 1 over 6. And then the concentration we have also converted, and then we have 5 here. Very interesting. Now, what are we looking for? The unknown is D half. Okay? Since we want to make D half the subject, okay, so it will become 607 times 2 times 1 to the power 2 over 3 times 4, 1 to the power 6 times 5, all over 50. All over 50. So that is what we'll have if we're now going to get what D half is. But diffusion current is not D to the power half. So if we are going to convert this to D, square root of D is equal to 50 over 607 times 2, which is N, times M, which is 1, 2 over 3, times T, which is 4, 1 over 6, times concentration, which is 5. So if you do all this multiplication, this is going to be 607 times 2 times 1 times 4 raised to the power 1 over 6 is 1.26 times 5. Now this is 50 over, if you carry out all these multiplications, you're going to have 7648.2. We're still working with square root of D. Remember, we'll have to bring this down to D. So if you do this arithmetic, this should give you 0.00653. So in other words, square root of D is 6.537 times 10 to the power minus 3. Therefore, D should be equal to 6.5, will approximate 4 times 10 to the power minus 3 all squared. And so when you get your answer, the unit for diffusion is cm per second. Thank you. So that is how you get your diffusion current using polarography. Now this is the problem we have solved. Now I'm going to look at the observations, but first of all, look at this polarogram. This is minus 0.6 volts. That's our applied potential. Now you notice that from 0 to minus 0.58, we have the residual current. Then gradually, it started increasing. So this sharp increase is where you now have your polarographic wave. So, and at this current, you notice that it is now constant. This constant current, we can extrapolate it to about minus 0.7 volts. Now, what I have shown you here is what we are going to see in the observations that have been listed for this experiment. Observation number 1, you see that in the polarogram I just showed you, there's a sharp increase in current at about minus 1.2 volts for HCl alone. But in the reduction of cadmium ion, you will notice that what I showed you was a steep rise. The residual current is considered as a baseline current which occurred at this region. But at about minus 0.6 volts, the current started increasing. And of course, we say this is due to the reduction of the cadmium ion. So until the reduction starts, your current cannot go up. You still maintain a baseline current, which of course we refer to as the RC. That's the residual current. But the moment the reduction starts at your microelectrode, you notice that the current begins to rise. Now, point number 4, as the electron is made more negative, you notice that the cadmium ions are reduced as fast as they reach the surface. When you go back and look at the plot we have, you know that the applied potential starts on a negative value 0.1, 0.2, all in the negative. So once it becomes, you increase the negative value, you notice that your cadmium ions are reduced as fast as possible until the electrode becomes completely polarized. Now the 5th point is that the current becomes independent of the applied potential at 0.7 volts. I showed you that. It remains constant, and at this point where it remains constant is what we refer to as a limiting current, because nothing else can happen. The reduction is complete. And then finally a sharp increase is observed from the residual current to the limiting current, and of course this is the polarographic wave, which is this. Now finally we are going to look at the applications of polarography. I have talked so much about polarography, so what is it really used for? What is this electroanalytical method used for? Now I have been able to list 3 for our own level. 1, a very large number of both organic and inorganic compounds can be reduced or oxidized at the polarographic electrode. And this has to do with a lot of field samples that we work on. And now we have a lot of environmental problems. And in some of these samples, you also have toxic metals. And so you don't want to do the regular analysis where you are exposed as an analyte to these toxic metals. So this is one of the important methods that you can use to do your analysis for organic and inorganic compounds. Secondly, simple metallic cations are reduced at the dropping mercury electrode to form the free metal or an ion of lower oxidation state. In some analysis or some work you want to carry out and you need that metal as a free metal, you can always do this, and then of course you obtain what you need to work with. Now, thirdly, the most important application of polarography have been in the area of determination of some organic functional groups, like the C-C bond, the C-O bond, the N bond, you have the C-S bond, and so on and so forth. So some of these functional groups, you can also determine them using polarographic method of analysis. We have come to the end of the lecture for today, and we are looking forward to continuing on voltammetry, because this is not all. We have a lot of other methods in voltammetry, in polarography, that we might like to look at. Next class we are going to look at what we call the DPP. We are also going to look at what we call the TPP, and we're going to look at the square wave polarography. These are different methods in polarography. This one is differential pulse polarography. Okay, and that is the classical pulse polarography, and this is what we call the square wave polarography. These are all methods that are employed in polarography. Thank you very much.